Chapter 11, Multiplexing and Demultiplexing, also known as channelization. Topics we're going to be covering are different types of multiplexing, whether it be frequency or time or some form of variation of the two, or code divisional multiplexing or amplitude. There's a lot of different types of multiplexing out there. Point of this is we're just covering a few of them. We're going to continue the discussion for data communication by introducing the topic of multiplexing. Multiplexing is such an important topic, and it's one topic that a lot of people don't get to have, and it really is a critical component for our data and our communications in general. To talk about its motivation, define basic multiplexing, and actually talk about modulation and modulated carriers. That's a big one. Not so much nowadays, but it was super important before. I mean, it's still super important, it's just not as super critical as the early 2000s. So the concept of multiplexing. Multiplexing refers to the combination of information streams from multiple sources from a transmission over a shared medium. So essentially what that means is taking and combining multiple signals to stick it on one signal. And on the other side, being able to separate those signals. A very quick, just brief overview of multiplexing. Think your broadband or cable provider. They provide phone, data, and TV on one physical or shared media. That's a type of multiplexing. Actually, they do it based off of frequency. They set a specific frequency for TV, specific frequency for data, and a specific frequency for phone. And that's how they're able to set all three of those on one media. And demultiplexing, it just kind of represents the separation. Here's the example. Multiplexing on the one side because it combines all of the signals. Demultiplexing on the opposite side because it separates the signals. So the basic approaches that we're going to talk about are frequency, wave, time, and code. The big two are actually time and frequency, but wave is also another form of frequency. It's just normally used for fiber optic, and the code division is more for cell phones or mobile phones. So, frequency multiplex division. We're assuming that you already understand frequencies and amplitude, modulation, things like that. So how frequency modulation works is it actually sets different types of filters or interference, which actually allow the separation of the different types of data. So for example, we have a 1000 megahertz capable media. We actually set so that every device might have 80 megahertz. We have a 20 megahertz band or protection on it. That way we can have up to 10 carriers. So essentially how that works is between 0 and 10 megahertz, it's a band. A band is just a protection barrier. Between 10 and 90 megahertz will be the actual frequency that data can travel. Then between 90 and 100 would be another band. And they just kind of stack on one another. But that way, the data that is going between 10 and 90, belongs to that specific type of mechanism. Going back to the cable provider, for example, that might be your audio or your phone system. So as long as it was between 10 and 90 megahertz, the systems recognize that is only for phone. So what happens if there's a jump or a spike or something that happens to the signal that changes it? That's actually why we have those guard bands. That band is there so that if it jumps over 90, it knows that's just abnormal and it kind of cuts it off. That way it doesn't interfere with the next frequency. That'd be the frequency between 100 and 110 being a guard band, between 110 and 190 being the next data, and between 190 and 200 would be the other guard band. That way, if it jumps from 90 megahertz to 105 megahertz, it's only a 15 megahertz difference, but it won't affect the other data sets, if that makes sense. So essentially, here is an example of our frequency division, and that is we have, well, this is the demultiplexing version of it, but we have one shared media. That one shared media comes into a demultiplexer, and then individual filters filter out those lines. Again, going back to the same example I just used, filter 1 might be the only filter that recognizes 0 to 100 megahertz. Filter 2 might be the only filter that recognizes between 100 and 200 megahertz, so forth and so forth. But that way, each of these filters will only be able to filter out their specific set of data. Going back to the cable example, you'd have 3 filters, one for phone. That way it would filter out all the information for data and TV. You'd have the second filter for data, so that filter would actually filter out everything for phone and TV. And you'd have a third filter that would be for TV, and that filter would filter out the data and phone. So what are some of the advantages of using frequency division multiplexing? It allows you to use the shared transmission media. It actually also allows you to break up larger types of cables that have high frequencies so that you can carry more data on it. That's actually a big thing, is being able to carry more data on one shared media. Now remember, going back to the practical frequency division, if the guard bands are too close, for example, there's only like a 1 megahertz difference between each of the data lines, might be too close, and it might cause issues. Hence why we have to have a guard band that's a little bit larger. But because most people are visual people, here's the example. I've noticed between channel 1 and channel 2, there is some form of space. That is what I meant by guard band. That's just a percentage of the cable that is set aside for protection. That way, if there's ever an issue with channel 1 and there's too much data or it spikes or whatever, it doesn't affect any other channel around it. Here's another example, just represented a different way. Here we have channel 1 using between 100 kilohertz and 300 kilohertz. Then there's going to be a 20 kilohertz difference between 320 kilohertz to 520 kilohertz. So here the guard band is 20 kilohertz. That again is just going to be separated between each of the different channels. Now, the actual guard band might be different in different situations. It really all depends on what you're doing. So don't take it as it's always going to be 20 kilohertz or 20 megahertz. It's just, it might be different depending on the data or the signal or the cable type that you're using. So one of the important things here is understanding why we do blocks or channels for frequency. So it's easier to break it up into organized connections. For example, the 100 to 300 kilohertz. We know that that will send off one specific set of data. Could be our voice, could be our data, could be our television, could be a specific type of data. And that means as long as you get those speeds or that frequency, you know exactly what it is. If we didn't organize it, then it would be a lot harder. One of the issues with frequency division is it is susceptible to noise, and that is any form of distortion or electrical current that will make that frequency be larger than its channel. There's two primary ways to dealing with the frequencies. And a big part of that is understanding the guard band. Here we talk about a K carrier. And pretty much the K carriers are just how many carriers you have, how many channels you need. And then the bandwidth is normally 1 divided by your K. So if you have 10 carriers, 1/10 of that is going to be your guard bands. So once we have one specific channel, we can actually do some form of frequency multiplexing again. So we can actually do subchannels. This actually helps with the immunity to interference because we start drilling down on our individual frequencies. So if we have a 300 kilohertz frequency range, we can actually subchannel them out. It's essentially contractors and subcontractors. You might have several channels, and then each of those channels actually can have subchannels. Think of, again, going back to the cable provider. They're going to provide phone, TV, and internet to a neighborhood. So what they might do is they might have 10 houses on that one physical connection. So within that one physical connection, there are 10 channels. Each house gets a channel. And then at each house has 3 subchannels. One for TV, one for internet, one for TV. That way, every house still has the 3 channels, TV, internet, phone, but there's only 10 main channels because there's only 10 houses. It's just a way to subdivide our connections. What about the hierarchy frequency division? This is the same thing, it's just a different way of organizing it. So here's an important one. So, what happens if we do 12 analog phone lines and we actually group them together so that we can have a super group or a larger group? So if you ever wonder about T1 lines, so T1 lines actually are 56K connections, and they just kind of bundle them together. And that's done as a hierarchy frequency division multiplexing. Or you can actually go the opposite way, where you have coming from the right going to the left of this diagram. You might have a phone company in an area give you a jumbo connection. That jumbo connection goes into a neighborhood, and then it starts breaking it down. Individual streets, and then individual blocks in that street. And that's how they are allowed to do the phone lines. Because actually this is a big one, how a lot of the ISPs work, is each neighborhood might have one of the diagrams on the left. So what ends up happening is your neighborhood would be grouped together, and then each neighborhood would be a super group, and then each major area might be a jumbo group, and so forth. Now let's talk about wavelength division multiplexing. So essentially, wavelength and frequency division are essentially identical. The only major difference is wavelength is more applicable to optical fiber. Essentially, instead of dealing with frequencies, as frequency is normally within copper cables, fiber optics use wavelength. Thus, wavelength division multiplexing applies to optical fiber. The input and output are the same mechanisms. One signal coming in multiplexed, one wavelength going out into separate different types of wavelengths. Demultiplexing, same essential setup. The major difference here, though, is instead of having different frequencies, we have different types of light. Hence why it will go through a prism, and then the actual different colors separate the different frequencies, because depending at what frequency the wavelength is, generates a different color. Sounds really complicated, but it really isn't. Here we have our multiple different types of data coming in, different wavelengths. It'll go through a prism, and it will be carried through one specific light. That one light comes out to another prism on the opposite side, and it is separated into the different colors. That essentially is the same thing with frequency division multiplexing, just with light instead of electricity. Next, time division multiplexing. Same type of system, except instead of going parallel, it's going sequential. And that is, assuming we have 3 senders, they take turns. So the first sender, the second sender, third sender, and they don't have unlimited. Like you have a 2-second window to send your data, and then it uses all of the bandwidth or throughput for that 2 seconds. And everyone gets 2 seconds before it repeats. But what happens if, again, it goes 1, 2, 3, 1, 2, 3, 1, 2, 3. What happens if at a specific point that 2 has no data? For those 2 seconds, all that bandwidth is being wasted. And so we have that issue that we're known as synchronous time division multiplexing, and that is round robin, 1, 2, 3, 1, 2, 3, 1, 2, 3, except here in our example, we're going to assume it has 4, just because our diagram has 4. So it's now 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. But again, what happens if one node or one device doesn't have anything to send? It's wasted. So I am building up to there's asynchronous, which that means not everything is round robin. If it notices 1 and 2 are sending more than 3 and 4, 1 and 2 get additional slots. And so it might go 1, 1, 2, 2, 3, 4, 1, 1, 2, 2, 3, 4. That way, 3 and 4 only have a smaller section or a smaller window. Most things used time division or synchronous time division multiplexing. But one of the issues is the demultiplexer didn't really understand where if we're doing 1, 1, 2, 2, 3, 4, it knows that the standard chunk is separated by very specific clock differences, but we had no way of changing that up. So that's why asynchronous had to be very organized. That way they had to agree that 1 and 2 would have 2 slots each, 3 and 4 would have 1 slot each. That way it would know the first 2 chunks of data would be for 1, the second 2 chunks of data would be for 2, the next chunk of data would be for 3, and the last chunk of data would be for 4. But we had to actually organize that. That way there was no misinterpretation of, again, if we organize it 1 getting 2, 2 getting 2, 3 and 4 getting 1 each, and we assumed it was all going 1, 2, 3, 4, 1, 2, 3, 4, we would have wrong types of data. Or we'd have misinterpretation of data. So what we had to do was some form of framing. Framing was just organizing or grouping of one actual completion. So in this example, 1, 2, 3, 4 would be framing. In the example that I kept bringing up, 1, 1, 2, 2, 3, 4. So we would have 6 different groups for our framing. So now that we talked about frequency division, time division, hierarchy, frequency division, wavelength division, we have one more. We have hierarchy time division multiplexing. This is actually in our T1 connections. If you'll notice that we have 24 DS0 phone lines. Those 24 DS0 phone lines made one DS1 phone line, or T1, then T2, then T3. So that's actually how we got our T1 connection speeds. We actually grouped 24 digital phone lines together, or 26 analog or 24 digital phone lines to make up our 1.544 megabits phone line. And again, there's a very specific hierarchy to this, so that for each level 1 or DS1, we have 24 DS0s. For each DS2, we have at least 4 DS1s, so forth and so forth. I went back, sorry about that. So now we can start talking about the problems. What happens about if there's unfilled data chunks? Here's the example. So computer 1 has 3 bits of data to send, computer 2 has 2, then computer 3 has 1. Within that structure, or within that time division, we're going to have some blank slots, and that is empty space. That means we have wasted throughput or wasted bandwidth because of the way the data was organized. So we came up with this statistical time division multiplexing. So it runs some form of statistics on the data, and then it recognizes that 1 and 2 might send the most data, so they're going to have the most slots, thus allowing us to maximize the data flow between all the senders. Though, with the statistical multiplexing, there's extra overhead, and there's extra demultiplexing overhead. And a big part of that overhead is some form of identification on the sender and receiver end. That way, the sender and receiver know which chunks of data it's sending out. So what about some form of inverse multiplexing? That is taking one signal and breaking it down to multiple, which we already talked about our T1 connection, and that's essentially what this is. We have a high-speed connection, 1.544 megabits per second, going over phone lines. So we actually had to break or inverse multiplex 26 individual 56K modems, or 56K connections, not modems. It will go through those 26 different 56K connections, and at the other end will be multiplexed together to form, again, one high-speed connection, or one 1.544 megabit connection. The important part here is they're not really backwards compatible. Like, we cannot inverse multiplex several pieces of conventional multiplex just backwards. It doesn't work like that. The inverse multiplexers are very specific. Alright, now that we've covered most of the basics, we have one left, and that is our code division multiplexing. And that is typically known in our CDMA, or our cell phone technology. And that is essentially, CDMA relies heavily on mathematics, idea of orthogonal vectoring space. That is not something that we normally have to deal with. Electrical engineers, mobile phone engineers, those guys have to deal with this. Normal PC or communication technicians don't. And that is essentially, it deals with a very specific form of multiplying of the sender and receiving to get several bits. For example, here we have a sender A trying to send 2 bits of information. The data value then becomes a very specific key, and the key might be different depending on who's sending it, how much they're sending. Here is the actual formula, and again, most people do not have to deal with this because this is for mobile phone or very specific electrical engineers, because this goes way more in depth than what we need to go. Anyway, that is the end of chapter 11. The CDMA is actually one of the most complex ones, and again, is not one that we typically have to deal with. If you have any questions, please let me know. If you have any concerns or issues, again, please let me know. Let me know how I'm doing so that if I can get better, I can improve. Thank you guys, and I hope you guys have a great day.
So I know this week is only chapter 11, and so I wanted to do something a little slightly different. I'm going to be doing chapter 9 from an additional data communications text, because I want to be able to focus on spread spectrum, because this is one of those important areas. Part of spread spectrum actually is things like dealing with jamming and interception, frequency hopping, and sequencing. When we start talking about our communication, one of the biggest things that we talk about is availability. But we don't always talk about confidentiality. And part of that is actually making sure that the signal can get where it's going, anti-jamming. Nothing can actually intercept and prevent that signal from going where it needs to be going. Again, all jamming. And some of the techniques that are used. A big part of that's going to be frequency hopping. I always start off week 4 with a frequency hopping question, just because it doesn't just have military applications, it actually does affect most of us in our everyday life. Our wireless, when the channels get overly saturated, how does the system know to jump frequencies to other channels? Big part of that is the actual frequency hopping. So, yeah. We're going to be talking about how the multiplexer actually gets fed from an encoder and a pseudo noise generator. That way the modulator can put it on the appropriate channel or channels. One of the benefits here is it will actually be broadcasting over a larger group of channels. That way the frequency can be hopping between them. It also allows for the spectrum to have greater bandwidth. The receivers are using the same sequence for demodulation. The demodulators is fed into an encoder. Essentially, this is what we're looking at. We do a channel encoder. That also is fed into a pseudo noise generator that helps produce the spread code, and then those get transferred over a channel. From those channels, the receiving end will actually demodulate it, and again will separate it back with spread code and our channel decoders. That way we can do an input and an output and have it modulated in such a way where it can actually traverse multiple channels, not having to rely on just a single channel. Because that's actually a really big thing, because when we have too much noise on several channels, or just a few channels that aren't evenly spread out, those channels get overly saturated. So let's talk about some gains for a second. So with the addition of gains, we're talking about the immunity from various noise and multipathing distortion. This means jamming. We're allowed to encode or hide or encrypt additional messages within our spectrum. Only the receiver knows the spectrum code. The important part there is, so when it gets sent over, the spectrum coding, or the spread coding, actually shows what portions of the spectrums are part of that encrypted signal. If you don't know what you're looking for, it makes it a lot harder to try to find it. Users that actually share the higher bandwidth, that things are our telephones, our CDM, our CDMA, our code division. You'll notice that chapter 11 was very heavy code division multiplexing. That's why I figured this tie-in chapter, along with frequency hopping, would be a perfect fit. So the next thing is, what are the pseudo-random numbers? So how do we get that random channel? So it actually is generated by an algorithm using an initial seed, our receiver. It actually is not truly random. It actually does it uses a deterministic algorithm, so it's not really random. That way we can actually use this type of algorithm to predict sequencing. So how does this tie back into frequency hop? Part of this frequency hopping sped spectrum, or FHSS, actually deals specifically with a seemingly random series of frequencies that are going to be broadcast over. It's not really random. It actually is done through a specific algorithm that allows best communication for those saturated frequencies. The receiver hops between frequencies and syncing with the transmitter. Again, it's not random. It is all actually very controlled. That way, if there's something like eavesdroppers, it's harder to see the frequencies that they're being changed to and from. Jamming on one frequency affects only a few bits. That means instead of having to jam just a few frequencies, for frequency hopping you'd have to jam several other frequencies, or you'd have to saturate other frequencies, thus no longer just affecting your one signal but additional signals. So that wouldn't really be very beneficial unless you want to jam multiple signals within an area, but that means you're going to be more noticeable. So this kind of depends on situation. So how exactly does this basically operate? So how we do this is, typically there's 2K carriers, frequencies forming 2K channels. The channel spacing corresponds to the bandwidth of the input, and they're using fixed intervals. 802.11 actually denotes the 300 millisecond interval. some of the numbers of bits transmitted using some encoding schemes. It can be fractional. So what exactly does this mean? Because when we discuss this, it's hard to see what exactly this means. So here's a graphical representation of it. So we are using our 8 different frequencies, and here they are in relative to time. You'll see there is a pattern to it. It's just first it might not be very seemingly, but there is a channel 5, 8, 3, 6, 1, 7, 4, 2. You'll notice that they're hopping between 1 and 8 channels. I would imagine that they'll also repeat afterwards. If they were using additional channels, we'd be actually hopping between those channels. So how does the actual transmitter work? Here we have our modulator, and it actually goes into a frequency hopping spreader, and a big part of that is our pseudo noise, our channel tables, our frequency synthesizer, and that actually allows us to do our filter out. Half a love the nitty-gritty of this. I've never actually had to use any of this. It's nice to know that it's there, and there is something behind it. It's not just this magic. It's actually very precise. If you're an electrical or a wireless engineer, you'd have to know this. But I figured it'd be at least a nice little peek behind the closet, just so that we can see what's really there. For the receiving end, same thing. We have our frequency hopper despreader, which is the opposite of our spreader, and then again our pseudo bit noise, our channel table, our frequency synthesizer, so that we can actually decode and get decode and demodulate, so that we have our output. So the next thing is, so for frequency hopping, can there be different speeds? There can actually be different speeds depending on our frequency hopping needs. I have to love the math here. Generally, the faster the frequency hopping, the better the performance in noise or jamming. Meaning, it's a lot harder to supplement noise or to interject noise or jamming for faster frequency hopping spectrums. The slower, the easier. That way you can actually target specific frequencies at a more steady pace. So graphical representation for our slow hopping is, this will be a function of time, and this will be a function of our frequencies, and you'll see that it's very slow per cycle. Now if we actually change that to our fast, we'll see that it's actually a lot faster within our time, and it's the same frequencies. It's just because of our time, we actually are able to actually switch that several times a second, making it harder to jam. That way you have to know the specific frequency that you're on in order to do that. Again, performance considerations is the larger number of frequencies used, the better the resistance to jamming. And to noise, because again, you're continuously jumping different frequencies, so the likelihood that the frequency that you're jumping onto will be saturated is really low. Even if it is saturated, the amount of time that you're going to be at that specific frequency is very low or short, because we're dealing with time. So the likelihood of you staying on a saturated frequency for an extended period of time is very low. The amount of time that you're there is, again, very low. So now we have this thing called direct sequence spread spectrum, and that actually helps in propagation. It helps with using wider frequencies. It actually also increases our frequency, or our bandwidth per frequency. Basically, it's very similar to our frequency hopping, but it doesn't do the same way. What I mean by that is it actually does not alter any of the spreading code bits, but what it does is it actually allows combination of our signals. And it's all in the methodology and how it does it. I've actually never used direct sequence spreading. Most of my training has all been in frequency hopping, but I just wanted to point out that frequency hopping is only one example of many. So now let's take a different look at our CDMA. And again, remember that our CDMA, it's just a multiplexing technique, and it's being used over a spread spectrum. And so what that means is we have several coding for multiple users, but that way we can share the same channel with an appropriate break. So here we have user A, B, and C represented into different message codes, and they're encoded in such a way where they're going to be different signals. So let's make the consideration that A is going to communicate with our base. So we know our code for A, and we actually want to send a very specific pattern. The decoder will ignore all sources when using A's code to decode it. Basically what we're doing here is we are looking at the combined messages, and we're seeing what we're going to have to decode and encode, because as we get 3 user signals coming through, we're going to start ignoring portions of the signal that do not match our filtering. So let's say that we have A, B, and C, and A, B, and C are actually communicating, and we only want to filter out filter A. We only want to see A. So it would be filtering out B and C. So the chip could actually do that one of two ways. It can filter out B and C, or it can filter A and just decode the A portion. Kind of just depends on the technique that is currently being used. Also depends on the chip that is being used as well. The CDMA is actually an N+ process, which means we can actually encode several users to one channel. It just every user is going to use its own P and frequency, or its own sequence, so that way our sender and our receivers will know how to decode whatever is being transmitted. Here's a graphical representation of our multi-in series frequency. Here would be our first user, our second user, our N+ user, any additional noise that would be filtered on our line. But how does that actually encode onto our using CDMA? And here we go. This is our encoding. Here we actually have our 7 users separated and sequenced in such a way we will actually use our channel 0 code. We will actually combine the signals, send them out. That way our receiver end can actually finish decoding them. And that's actually this chapter in a nutshell. It's always interesting to start looking at how our sending and receiving chips actually truly function. Normally, if you don't have a good understanding of digital logic, some of this is not the easiest to learn. But at the same time, we're not electrical engineers, so we don't have to understand it to this nitty-gritty. But I just thought it would be interesting to share, because a lot of people always ask questions about how this really functions, and they always think that it's all very scary, but it really isn't. This is just, again, a very simple overview of how most of this works. And thank you. I hope you guys have a great day. Okay, so I wanted to discuss some follow-up items. One of the first things is our APA formatting and citation. That goes for both our IPs and our discussions. Remember that we have to do all of our work according to APA manual. So if you're not sure how to do that, go online. You can type in APA formatting. If you don't want to look it up online, you can go to any of the tutorial services. We have a writing, we have a library service. They can give you additional resources on how to do APA formatting. That's important. That's not going away. In discussions, same thing. We have to be doing our citations in our discussions, because one of the big things is, for our citations, we're building off of other people's works. So it's a way for us to verify what we're claiming is supported by the literature. So when I say something at the sky is blue, you can take my word for it, or if I provide a citation, you can take an expert's word for it, and then I built off of that. So it just kind of increases your credibility. We should be at least citing in every post, or as much as possible, because again, we're trying to link what we've done back to the literature. Same thing in our IPs. Every paragraph should be tied to a source. Every paragraph is an idea, and every idea we need to have support within the literature. And I know at this level it's not that big of an issue, but you want to get in the habit of doing that, so when you start doing higher level work, it's second nature. Also, length. We don't need posts that are great job. I mean, don't get me wrong, it does add to it, but when I start grading for posts, I'm not doing full credit for those that have 3 posts and 2 of them are great jobs. I don't count the great jobs as a post. For our discussion board, I'm looking for 3 solid responses with citations. For our papers, I'm looking for 3 pages of content with citations. So what I mean by content is, that's 3 papers on topic. That's not a cover page, that's not your reference page, that's 3 content pages. 2 if you're really good, but I'm really looking for 3 if you're doing diagrams. Diagrams totally are okay, as long as you're doing them within APA formatting. Lastly, grading. Again, I grade heavily off of attempt, like if you're putting an effort into it. Like if you did 2 pages and you did a few citations, and I could see that you were making an effort, I'll meet you. But if you post once, or you did a page and a half with 1 citation, that really isn't you making an effort. If you get stuck, don't get me wrong, some people a page is a lot. If you get stuck, you have plenty of resources to bolster up your paper. You can contact me, I'll help you. If you don't want to contact me, we have a writing center, we have a tutorial center, we have plenty of help for you to get. If you need tutoring, there's a lot of tutoring out there. And again, provided from the school. All you have to do is say something. For our tutorial lab, we have tutorial services for SQL, we have tutorial services for database, we have tutorial services for math, English, writing, research, library services. I mean, we have a great amount of tutorial services. And if we don't offer tutoring in a specific area, you can ask for it specifically, and they will find tutors for you. So you could not get tutoring, because you can. If you ask for help, the school will get it. If you cannot get it from the school, there's other help. I will sit down with you. I will do as much as I can with you if you need one-on-one. If you need tutoring and you don't get tutoring, that's not a failure on my part. That's not a failure on the school's part. That's only a failure on your part, because there's plenty of opportunities there. You have my number, you have my email, you have 2 emails from me, you have my cell phone number, you have plenty of ways to get a hold of me if you need help. And again, if you don't capitalize on help and you need help, that's on you. Because Okay, there's plenty of help out there. All you have to do is say something. Thank you.